Good morning, everybody. I'm going to finish the last notes from the single slit and resolution note sheet. This is on resolvance, which is related to resolution. They have the same root word. This is a specialized topic particular to the IB, but I'm going to teach it to you regardless of whether you're in the AP or the IB. It has to do with a diffraction grating, which remember is not just one or two slits, but many, many slits, and its ability to resolve the different spectral lines. So I'm going to refer to a video from YouTube just to kind of give you a better context before we get into the equations and the idea behind it. Okay, so what you see before you is a simple neon light, not the best quality video, it's all I could find. And so let's look at it through a diffraction grating, which is something you did in class for the lab. All right, so I'm going to pause this video here. So if you look off to the right, you can see, again, it would be nicely darker. You see these, especially in the reds and oranges part of the spectrum, you see the lines are very fine and they're very close together. So your ability to distinguish one distinct line from another is limited by the diffraction grating itself, and that's what the idea of resolvance is. In other words, if we had a better diffraction grating, and again, ignoring the video quality of this, we might be able to distinguish 10 or 15 lines in the red to yellow part of the spectrum, whereas with the diffraction grating we see here, or even class, you might have been able to only resolve 3 or 4 or 6 lines. So since diffraction gratings and the ability of that to take a light source, especially in astronomy, and break it into individual components is an extremely important and useful tool, the IB program felt that it was important for you to understand it. That's my best guess as to the motivation for them asking us to teach you this. Okay, so with that in mind, let's just give you the nuts and bolts. There is a section in your reference tables that talks about where these equations can be found. It's not like you have to memorize them, and I'll point those out in class. Okay, so what is resolvance? All right, it's the limit you get from a diffraction grating. Okay, ability to separate different wavelengths or frequencies of light. Okay, so we're going to find a quantity called resolvance, capital R, not to be confused with resistance. All right, so the definition of resolvance, capital R, is the wavelength in question that you're trying to resolve divided by the difference in wavelength between two successive lines. Okay, so we have the wavelength there, lambda, delta lambda, the smallest possible resolved distance. In other words, how tiny of a distance can we, or a wavelength can we distinguish in an eventual or possible or hypothetical, that's the word I want, emission spectrum, like you saw for the neon light. Okay, so resolvance doesn't depend on lambda over delta lambda, just like resistance doesn't depend on voltage and current, which is this definition, but it depends on the diffraction grating. Okay, so the diffraction grating puts a limit on that, and the equation, the relationship that relates that is a simple equation, m times n. Okay, and we define what that means here. N is the number of slits illuminated. So if we had a diffraction grating in the lab that had 10,000 lines per centimeter, maybe it was millimeter, right? And the grating was 1 centimeter across, that's quite a few number of lines, and we got to make sure they're emitted. And then m is whatever fringe number that we're looking at. Okay, so if I have a screen, right, we'd have the central bright spot, which would be the 0th fringe, and then we might have the first fringe, which would have red. Oh, I should be careful about that, right? Red would be further away than blue, and then there's our spectrum between blue and the red. Okay, so if I want to then, ultimately what we're interested is what is the minimum number of lines, or what kind of diffraction grating we want if we want to be able to distinguish two very close lines as defined by the delta lambda. And that's generally how it works. So let's just do a quick little example. Okay, so let's say we have a source of sodium. It is put under high voltage, which causes excitation of the electrons in the atom. And there are a multiple number of lines. We're interested in 2 green lines, okay, that have a very precise wavelength, 589.00 and 589.59 nanometers. Okay, we could ask what is the resolvance. Why we care about that is ultimately what is the minimum number of diffraction grating lines that we need to be able to actually see the distinguish between them. So it's pretty straightforward. I think the hard part is just really understanding the cause and effect, or the essentially the cause and effect in the context in which you would apply this. So since we're given lambda, and if you will, lambda prime, we can calculate resolvance as simply equal to lambda over delta lambda. So we're interested in the 589 line, okay, and then the difference between them, okay, 589.00, so you can see why we have to be so precise, 589.59. I'll work out the math for you, and this turns out to be 1,000. So the resolvance that we're shooting for is 1,000. So now we could ask, in order to see the second fringe, all right, why the second fringe in this case? Well, why not? So that's M, that's N. So we can see that the N, which is what we're solving for, is simply equal to resolvance over M. So that's pretty easy. That's 1,000 divided by 2, which is 500. So 500 lines have to be illuminated in our particular diffraction grating. If we wanted to see the first fringe, then you'd have to use 1,000 lines. So maybe that's why we want to look at the second fringe, because it's a lot easier to illuminate 500 lines than it is to illuminate 1,000 lines. Okay, that's what I have for the resolvance. I think there's a problem or two on your homework that asks about that.